I love it. I love it. And we're going to talk about the law of truly large numbers now. So this says that with a large enough number of opportunities, any outrageous thing is likely to happen. And David, I don't know whether it's worth kind of explaining how this differs from the law of large numbers or large numbers in general, because people might get these two things confused. Truly large numbers and large numbers are different things. So,
Yeah,
yeah.
yeah, that's a very good point. The law of truly large numbers is the one that people generally think of when they think of things like the improbability principle. Okay, but let's start with the law of large numbers, the standard thing that you find discussed in any statistics or probability textbook. The law of large numbers, without the truly, basically says that if you take a sample of measurements, throws of a dice or something like that, and take the average of that sample, and then take another sample of the same size and take an average of that sample, and another sample of the same size and take an average of that sample. The larger the samples you get, the closer the averages are going to get to a particular fixed constant value, which we could call a probability. But that's what the law of large numbers. It's a sort of a property of nature which says that things converge to a particular value the more times you do them. So let me refer back to one of my earlier examples, flipping a coin. It might come up heads or tails. When I flip it first, let's call heads 1 and tails 0. So when I flip it the first time, my score is either 1 or 0. When I flip it a second time, I could get 2 heads, so 2 ones with an average of 1, or 2 noughts with an average of 0, or it could come up heads or tails, and it can do that two ways, because it could be heads and tails or tails and heads. The average of those, when it's a head and tail, or 1 and a 0, is a half. So now I've got not just it's going to be 0 or 1, it's going to be 0 or 1 or a half now. And the probability of being at half is twice the probability of being a 1 or a 0. And as you do that, so things get closer and closer to the half. The binomial theorem is the relevant piece of mathematics which describes that particular illustration. So the law of large numbers, repeated things, calculating averages tend to converge to a particular value. The law of truly large numbers is very different. Again, let me kick off with an example. You described, you expressed the law. The law says with a large enough number, truly large number, of opportunities, any outrageous thing is likely to happen. What it says is you've got something which has got a tiny chance of occurring, but if you keep trying and keep trying and keep trying, you'll get there in the end. This is so winning the lottery is like that. If you keep playing, you take the 649 lottery I was talking about before, a 1 in 14 million chance if you buy one ticket of winning. So you buy one ticket, you're going to lose. You buy another ticket. You keep going long enough, you're basically certain to win it. Give it enough opportunities, you're certain to win. By one after the other, I spent maybe millions of years, but buying, 14 million tickets and then another 14, I'll get there in the end. So a classic example of this is someone winning the lottery twice. Clearly, that is an astronomically improbable event. But if you think about the number of lotteries there are around the world, the fact that they're repeated week after week, sometimes more than once each week, you think of the number of people playing the lotteries, you see that people buy more than one ticket, you see that astronomically small probability has been given so many opportunities to occur, people winning a lottery twice, that you'd expect it to happen. And in fact, there are, it would be, the probability is almost zero, essentially, that people won't have won the lottery twice amongst all those opportunities. And indeed, it has happened. There are people who have won lotteries twice. There are several documented cases of this, which always seems grossly unfair to me because I haven't won it once. There you go. Right at the start, I mentioned the example of going on holiday and bumping into your neighbours from home. Now, when that happens, you think, wow, what a coincidence. Imagine that. What are the chances? But you also think the same if you bumped into a family member, a work colleague, someone new from shops and so on. And now the opportunities are building up. The larger the numbers, the more often you go on holiday, for example. If you go on holiday every week, your chances are building up. There are many, and countless other examples of this law of truly large numbers. Bullets being shot into the air during celebrations in some parts of the world, for example, killing somebody when they come down. And maybe that isn't so surprising, but it's been documented. Or the case of 26 black numbers coming up in roulette, one after the other. 26, or the red and black numbers. There are equal numbers of red and black, so the chance of getting a black number is a half. But it happened one after the other 26 times. Happened in 1913 in Monte Carlo. Or what I referred to earlier, me encountering another David Hand. I used to go to a lot of conferences, and let me take a step back. I think I referred to the optician where I met another David Hand, but that's not the first time I've met another David Hand. The first time it happened, I was at it was 2012. I was at the Royal Statistical Society conference. I went up to the reception desk in a hotel to register, and I said, "My name's David Hand." And the receptionist looked at her screen and said, "But you've already registered." And I said, "No, I haven't." And she said, "Oh, I see what's going on. There's another David Hand here." And she then asked me a question which at that time I'd never been asked before. She said, "Which one are you?" And I said, and this is what I have to say, in all honesty, this is one of the only two quick thinking moments of my entire life. I said, "The real one, of course." She wasn't impressed and said, "They all say that." But anyway, the point about that is, when that happened to me, I thought, wow, what's the chance of me bumping into another or meeting another David Hand? Actually, it's happened to me 3 times now. No, anyway, but if you think about it, the law of truly large numbers. At that time, I was going to a lot of conferences. Maybe went to 20 hotels a year. Each of those hotels would average of 400 people staying in them. Which would turn over during the course of the week or whatever. So it'd be more than that. The chances are that, there are a few hundred David Hands in the UK, I think. The chances of one of the others being there and the hotel receptionist spotting the similarity or seeing it on the computer, it's beginning to build up. I'm giving it, the chance, any one of them is very unlikely, but I'm giving it so many opportunities to build up. And the same with the roulette wheel. The number of games of roulette which have been played around the world is vast. So, although 26 black numbers coming up one after the other is tiny, so many opportunities for that to happen, you should expect it to happen. This sort of thing occurs all over the place. In physics, they call it the look elsewhere effect, because what happens there is they look for a particular value for certain numbers. In fact, they're looking for a bump in a spectrum. And if it's not there, then they will look elsewhere for it. And if you look in enough places, you're giving it lots of opportunities to find something which appears to be significant. And there's a well-known classic case. There are many examples of this, but one well-known classic case is a young girl, 10-year-old Laura Buxton, her name was, who took part in a balloon race. You release a balloon with a label, a message tied to it, asking the finder to return it, saying where they found it. She did that, took part in a balloon race. The balloon went up. It was found 140 miles away by another Laura Buxton, somebody with the same name. But if you think about the number of these things which happen around the world all the time, every year, it's be surprising if that had never happened. So that's the law of truly large numbers. Give a tiny probability, enough opportunities to happen, you should expect it to happen. That was a long explanation. Sorry.
No, don't be sorry. It's absolutely fascinating. This is great. If you enjoyed this clip, then head on over to Locals to access the full conversation right now. Supporters can access the video version, and everyone can access the audio-only version of the conversation. I'll see you over there.